Okay, Mr. Metz here again, ready for our lesson 1.4 on combinations. Before we just get started, I wanted to let you guys know, okay, so I'm sitting in room 205 upstairs in the corner of Cambridge Sandy High School, and I'm standing in an empty room recording these videos, and I sure wish you guys were all here. It's kind of a bummer sitting here. I thrive on the interaction with all of you guys, and it's well, to put it bluntly, it kind of sucks that we're not all together, right? It's kind of a bummer. But anyway, that's my commentary. I hope this is going okay for those of you that have internet access and can access Schoology. I'm giving it my best shot at trying to get most of the curriculum put up there for you guys for the rest of the school year. Um, for those of you that don't have internet access, at the time that I'm recording this video, I'm not sure how we're going to handle that, but I hope uh, I hope that we get it figured out at some point how you can continue your school year. So at any rate, let's go ahead with lesson 1.4, the lesson where we learn how to count with combinations. I haven't really mentioned it yet, but there will be a test for you to do on this unit on counting. So um, just kind of a summary here. Hey, actually, even before we do that, we're trying to learn how to count and determine the size of a sample space, and it's all because what follows in this course in the next couple of weeks is calculating probabilities. And we haven't really defined what probability is. If we would all be here, like a normal classroom setting, we would have covered this already. But this word probability, I guess in our discussion so far, I haven't really defined this. So, I mean, let's keep it super basic. Probability is, I'm going to use the word chance. It's the chance that something will happen. The chance that something will happen or occur. There we go. We'll keep it basic. The chance that something will happen. And when we calculate a probability, we're going to have a numerical value that describes that chance. So to calculate those numerical values, the chance that something will happen, we need to be able to count. And that's what we're doing in this first unit, is learning how to count, how to determine how large a sample size is for an event. So we start the chapter dealing with sample spaces, where you just try to list all of the outcomes. And in the previous lesson, you see here again, here is a tree diagram that shows us if we're picking out our milk option and our cookie option, that we really end up with 4 possible outcomes. And we've got a tree diagram that shows us those outcomes. Here's another tree diagram. Again, wow, this person got bored and didn't finish, but maybe they didn't finish because they knew the fundamental counting principle says if we have 2 options for bread and 3 options for the meat, ooh, what would those be? Ham and what's T? Um, T, anybody? Oh, turkey maybe? Ham, turkey, and bologna, or ham, turkey, and bacon, or something. But anyway, 3 meat options. And then for cheese, it's S or A. I don't know what that is, Swiss or American maybe? So this person probably didn't finish because they know the fundamental counting principle just says multiply these options together, 2 times 3, which is 6, times 2. which is 12, and there's going to be 12 outcomes over here in the entire sample space. And the top outcome was, I don't know, WHS, what's that? Wheat with ham and Swiss cheese, I guess. So we started with sample spaces, and then we moved on to this counting technique, the fundamental counting principle. And then we had our little 8-point quiz, which I think you probably completed already by the time you're listening to this. And then we talked about permutations as well. So the last lesson, it maybe wasn't yesterday for you, but it was the idea of permutations, and you worked on 13 practice exercises and submitted that to me. So the permutation idea was the idea that when order matters, when the order is important, like in this case, if A and B is different than B and A, or if C and A is different than A and C, these are 4 possible permutations here. I guess, should we continue to list? When I'm looking at the notation here, it's telling me there's 3 total items, and from those 3 total items, I'm gonna choose 2 of them. So I started my sample space right here. I could choose A and B, or B and A, or C and A, or A and C, or what's left? Would B and C be an option, or C and B be an option? I'm feeling right now, sorry for writing right over top of this, I'm feeling right now that there's 6 permutations, but let's try the formula just as a quick review. 3 permutation 2, that means N is 3 and R is 2, and the formula says N factorial over N minus R factorial will give us the size of the sample space, the number of outcomes. So here we go, 3 factorial is the numerator, and the denominator is N minus R, 3 minus 2, which is 1 factorial. And we know 3 factorial means 3 times 2 times 1, and 1 factorial is just 1. So it looks like I've got 6 on top, right? 6 over 1, which is 6, and it's those 6. And in the last lesson, we also learned that we could use our calculator to calculate 3 permutation 2. We know we're going to get 6, but let's see, we go 3 and choose the probability key, and then select NPR for permutation. And whoops, not 6, my mistake. And out of those 3, we're going to select 2. So you type 2, and then hit equals, and it should also say 6. So that was the last lesson, counting with permutations, and you can only do that when the order matters. So one more permutation problem, at least I think it's a permutation problem. If you're running in a race, isn't the order important to you? The order of finish is important. So I'm assuming it is here for these runners as well. And in this case, there are 50 elite runners that are running for prize money, and it's only the top 3 that we're worried about. And the order is important. That's why I chose permutation in this scenario, because the order is important. So 50 permutation 3. I'm going to determine this with the formula instead of my calculator. It's going to be 50 whoops, let's try that again. It's going to be 50 factorial over N minus R, 50 minus 3 factorial. and 50 minus 3 is 47, so it's 47 factorial. And when I think about this, 50 factorial is 50 times 49 times 48 times 47, and yada, 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 all the way down to 1. And the denominator is 47 times 46 times yada, 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 all the way down to 1. And if we cancel out common factors in numerator and denominator, I can see here, I'm going to cancel out everything except 50 times 49 times 48. I don't have, oh, I do too, have a calculator here because I'm too lazy to multiply that on paper. So it's 50 times 49 times 48. Pretty sure it's 117,600 possible arrangements for the way the top 3 finishers could occur. That blows my mind, actually, but it's over 100,000 ways. Okay, let's order a pizza. Dang, that actually sounds appealing right now, ordering a pizza. In this scenario, it's got to be a 2-topping pizza. Do you think right now, if you grabbed a piece of notebook paper or scratch paper, that you could list the whole sample space for ordering a 2-topping pizza? Maybe you even want to stop the video right here and do that. Here's your 4 toppings right here: pepperoni, sausage, onions, mushrooms. Why don't you stop the video and list the whole sample space? Okay, in doing so, I'm wondering how big your sample space was. I'm gonna guess that a bunch of you said there's 12 options for ordering the pizza. Did any of you say 12? If you said 12, maybe it's these 12 options. I could have ordered pepperoni and sausage, pepperoni and onion, pepperoni and mushroom, or sausage and pepperoni, and so, whoa, wait a second. Is pepperoni sausage the same as sausage pepperoni to you? Or are you super picky about how your ingredients are put on your pizza? I think in this scenario, the order doesn't really matter, and pepperoni sausage and sausage pepperoni are the same thing. So I think in this scenario, we cannot do 4 permutation 2. Can't do 4 permutation 2 because order doesn't matter. And in permutations, order matters. So I don't think there's really 12 options either. So how many options are there? Come on, think about it. Think about it. You know, it's not 12. It's actually, right. Okay. So, wow, let's skip that screen. I don't like that. So we can't count with permutations. There's another way to count in probability. It's called combinations. And you can count with combinations when the order is not important. If pepperoni and onion is the same as onion and pepperoni, and this is really just one option and not 2, it's not 2, it's one option, these are really the same thing, then we count with combinations instead of permutations. So in the scenario, I don't know what the scenario is here, but if ABW is the same as BWA, then you're talking combinations. It's the same same combination of 3 letters. Here's a good example. So you have 3 ideas for birthday gifts for a friend. You've got a friend, got 3 birthday gift ideas, but you only have enough money to buy 2. So you're going to buy your friend 2 of those gifts. How many options have you got? Let's say those gifts are, and here they are, a gift certificate to Applebee's, a theater tickets, and a calculator. That's your three options you're thinking about, and you're going to buy two of them. Wow, I don't know, that Applebee's certificate's not going to be worth diddly dog, is it? Oh, come to think of it, the theater tickets aren't going to be. Maybe your friend doesn't want any of those. I'm not sure, but let's pretend that they're valuable, and they will be. They will be at some point. So those are the three things you're thinking about: the gift certificate, the tickets to the theater, and the calculator. And you're going to pick two of those. So let's do the whole sample space. I bet, stop the video, list the whole sample space of picking two of these three items for gifts for your friend. Well, my sample space would look like this. It's not very long. I could buy the gift certificate and the tickets, or the tickets and the calculator. I would want the calculator myself, or the calculator and the gift certificate. I would not list calculator and tickets here because this is calculator and tickets. It's the same combination of the two, and the order doesn't make any difference. The dudette is getting the same two gifts. So I'm pretty sure the sample space only has three outcomes in it. And in this scenario, we can count with combinations, and it would look like this. We have three total gifts, and we want to buy any combination of two of them. Three gifts, we want to buy any combination of two of them, and it would look like this, notation-wise, in the probability world. And there's a formula that we can use for n combination R, and it looks a lot like the permutation formula with one difference. It looks like this. Remember the old n factorial over n minus R factorial? That was the formula for permutations. Well, the combination formula has an extra R factorial that's multiplied as a factor down here in the denominator. And so 3 combination 2 would look like this: 3 factorial over 2 factorial times n minus R would be 3 minus 2. 3 minus 2 is just 1. So this would be 1 factorial in there. So it would be 3 times 2 times 1 over 2 factorial, which is 2 times 1, times 1 factorial, which is just 1. And in this case, it would be 6 over 2, which is 3. And we knew it was 3 because you already, didn't you? You did, didn't you? List the sample space before, stop the video and list them. And so there's only 3 combinations. So counting when the order is not significant, you have to count with combinations. And there's a combination key on your calculator. You've seen it, right? If you hit the PRB key, then right after the permutation symbol, there's a combination symbol. And wasn't it the factorial one that comes right after that? So if you use your arrow key and hit PRB and slide over to combination, you can use your calculator. And again, the formula for the combination of n items R at a time is n factorial over R factorial times n minus R factorial. The formula is a little cumbersome, but the calculator makes it easier, and you can do them easy way. Either way. Hey, by the way, if you, oh man, I can't remember now, 7 permutation 4. I'm gonna use my calculator here. Wow, 7, hit PRB, 7 permutation 4. Oh yeah, I remember now. This has a value of 840 and 7 combo. Wow, can you do it on your calculator? Give it a try. 7 combination 4. What'd you get? What'd you get? Hey, what'd you get? I got 35. So how many times greater is 840 than 35? Well, let's see. 840 divided by 35 is, I'm sitting here with a calculator right now. Let me try it again. 840 divided by 35. I got 24. 24 times bigger. The number of permutations is 24 times bigger than the number of combinations. Remember in the pizza problem back here, the number, where'd it go? Where'd it go? Here. The number of permutations was 12, but the number of combinations of 2 ingredients was 6, and the number of permutations is twice as big as the number of combinations. And then in this problem, the number of permutations is 24 times as big as the number of combinations. Well, the question is why? Why is it that way? We do know the number of permutations generally now. The number of permutations is going to be greater. Is that the greater? Greater, yeah. Number of permutations is greater than the number of combinations. Or let's put some concrete numbers. 5 permutation 2 is going to be greater than 5 combination 2. Permutations is going to be bigger. And if you think about it, it would make sense because remember the combination formula? The combination formula has that extra r factorial. And in this problem right here, r is 4, right? So we have an extra 4 factorial right here. And 4 factorial is 24. There's an extra 24 in the denominator. And what happens to the value of a fraction when the denominator gets larger? What's happening to the value of this fraction when the denominator gets bigger? Yeah, it's getting smaller and smaller and smaller, right? So this 24 makes this answer 24 times smaller, 24 times less. 35 is 24 times smaller than this. So the number of permutations, the number of combinations, generally the number of permutations is greater. But how many times greater? It all depends. It all depends on R, the number of items chosen out of the total. Okay, so let's skip that. We don't need that. Okay, so your exercises in your very short assignment here are going to look like this. Logan, he's planning on going to a trip to Duluth. He's going to bring 3 of his Man's Mall t-shirts like this. He's going to bring 3 of those. And he's got black, red, green, blue, and orange. He's got 5 of those things. He's going to bring 3. Okay, so how many options does he really have? So let's think about it. If he brings black and red and orange, is that the same as orange and black and red? I mean, that's the same thing, right? He's got the same 3 shirts in his duffel bag. So I think the order is not important. So when I think about permutations or combinations, the order is not important. I have to count with combinations. So he's got 5 shirts and we want any combination of, lost track here, any combination of 3. And so I'm going to use my calculator now and I'm going to go 5, hit PRB. Maybe you're doing an online calculator. 5 PRB, choose combinations, tell the calculator there's 3 shirts that he's going to choose. So 5 probability, choose combination, hit 3, 10. I got 10. Did you get 10? I think it's 10. Big bully Brandon only has 3 friends, probably because he's a bully. His parents say he can bring 2 of them to his birthday party at McDonald's Playland. Are you feeling how many options he's got? He's going to bring 2 of the 3. How many ways can he pick the 2? Let's just say it's friend A, friend B, friend C for lack of creativity. He's going to pick 2. Well, how many ways? Let's list the sample space. Do it yourself. You can do it right now. Pick 2 of them. Maybe A and B. Well, what's another option? Well, he could bring B in. No, wait. B and A would be the same as A and B. Oops. Okay, so A and B, or B and C, or there's only one other option, right? Or C and A, or A and C? I think it's only 3. The order doesn't make any difference, right? So this is a combination problem. So 3 combination 2. And try it on your calculator right now. 3 combination 2 is going to give you 3. It's those 3 combinations. Okay, so critical ideas. What's a combination in statistics? You should know at this point, a combination is an outcome when order does not matter. I'm running out of room. It's an outcome when order does not matter. How does a combination differ from permutation? Okay, combo, order does not matter, and in a permutation, order does matter. So that's the difference. Ooh, another good test question. What's the formula used to count the number of outcomes if they can be called combos? So that's a good test question. What's the formula for combos? N factorial over, okay, R factorial, N minus R factorial. And these 2 values are being multiplied together right there, right? Can you use your calculator to count with combos? I hope you're saying, yep, I can do it. Most of you can. Okay, your assignment is going to be, and you'll see it in Schoology, your assignment is turn to page 18. There's page right there. Turn to page 18 and work on those exercises. Put your answers on Google Doc or piece of paper and then shoot it my way, submit it on Schoology, and I'll take a look at it. That's it for lesson 1.4. Hope you guys are healthy. Bye.